Welcome to Chapter 13. We will be starting with free radical reactions. So we'll be talking about radical reactions. And that is where we'll start for the Organic 2 portion. So this is a review slide from Organic 1. And this is an alkene starting material. So you see with HBr, and this is electrophilic addition. And if you remember, I just write EA for electrophilic addition. And so this means this nucleophile will first attack the electrophile to give you the more stable carbocation. And so the regiochemistry there then would be the proton goes to the least substituted to give you the more stable. This is a benzylic carbocation. So the benzylic will not rearrange. And then your bromide nucleophile will now attack the carbocation electrophile to give you a Mikharivnikov addition product. And so that brominates the more substituted benzylic position here. So A is your answer. Okay, like I said, welcome to Chapter 13. So we're dealing with radicals. And so what is a radical? If you see here, it's a half, we call it a fish hook arrow. And these electrons here in this double bond are going to do a homolytic cleavage. And so that's a homolytic cleavage. If you want a Pogel exercise that kind of talks about this, you can do Pogel 6a and Pogel 6b. I think it's 6a. So this is the half-headed arrow. And this is a radical. Radicals are not charged. There's no ions. There's no cation or anion. So the structure of a radical is sp2 hybridized. So this means that this one electron here is going to be in an unhybridized p orbital. And so the unhybridized p orbital is above and below the plane. The R groups, so the hydrogens here, are all flat, planar, and they're 120 degrees from each other. Now, keep in mind that this would be kind of like an electrophile from the standpoint you see when I do this empty orbital, because how many electrons does an orbital hold? 2 electrons. And so if you see this, you'll see that the radical has this empty p orbital that only has 1 electron. And so it can hold a second electron. And that's the chemistry you're going to see. Now, you'll see BDE, which stands for bond dissociation energies, and these can be measured. So you can actually look in the back of the book or appendix or look these up. You'll see bond dissociation energies for each one of these particular types of bonds. And so here we have a bond dissociation energy of 410 kilojoules per mole. These have all been measured. Here a secondary hydrogen, so that hydrogen is bonded, that carbon's bonded to 2 carbons, is 397. So this costs less energy. And the word we're going to talk about is abstract a hydrogen. So when you're doing a homolytic cleavage and you're abstracting a hydrogen, you consider the bond dissociation energies, and the lower the bond dissociation energy, the easier it is to abstract that hydrogen. And that's what we're going to be doing, is taking this hydrogen to generate a radical. So this is a primary radical, 410 kilojoules. This one's 397. A tertiary radical, we don't have it on here, is even easier to abstract a hydrogen. So you're going to see that this follows the same pattern, follows the same pattern as the carbocation stability. And it should make kind of sense because you're talking about an electron deficient carbon and a carbocation. This is a carbocation. Has this unhybridized p orbital. It's sp2, and it needs 2 electrons. So you have a nucleophile that comes in with its 2 electrons. It's going to go into that empty orbital. Well, here you have an electron deficient unhybridized p orbital with 1 electron. How do you generate these free radicals? You're going to need either heat, which is you'll see across the reaction arrow is a triangle, or light, which is h nu. If you remember from general chemistry, E equals h nu. Nu is the frequency, E is energy, H is Planck's constant, and that means light of a certain wavelength. And so I think it's usually blue light you'll see can generate a free radical. A lot of times you'll see peroxides. So if you looked up the bond dissociation energy between the oxygen, you'll see it's weak. So you can get homolysis. Homolysis means the homolytic cleavage, which each one of these split to make 2 of these oxygen radicals. You see this with hydrogen peroxides. This is how hydrogen peroxides react. All right, so the mechanism here, I do expect you to be able to draw a mechanism for your assignments, assessments, mechanism. And the first thing you have to do, the mechanisms are going to be kind of different. You're going to list them. You're going to have to, the first step is initiation. So you'd want to be able to write the word initiation. And then you show that. So this is an initiation reaction. You have, actually this is a propagation. The next thing you're going to have is propagation. Usually you have at least 2 propagation reactions. You've seen stuff like this in Hess's law, when you're doing Hess's law reaction mechanisms in general chemistry. So initiation requires the generation of a radical. So this is showing that the halogen free radical has been initiated. And then propagation, sometimes you'll see me say P1 or P2. That means propagation step 1, propagation step 2. So this is a propagation step 1 where the free radical then goes and extracts this hydrogen to make a new bond. So you see this is the new bond, and then you generate the radical, the new radical. This is important because we care about carbon. This is organic compounds. So organo compounds, this is your carbon radical. And this is where we're trying to functionalize. So functional groups, right? Functionalize the carbon. So if you see, this is an alkane. And you're going to see that we're going to go from an alkane to an alkyl halide. There's not that many ways to functionalize an alkane. Alkanes are non-reactive. They don't have any functional groups. But this way we can make an alkyl halide. And you know those undergo SN1, SN2, E1, E2 reactions. All right, so another way you're going to see these free radical reactions is the free radical with a double bond. So if you add this free radical, this is after initiation. So we have, so this then would be a propagation step. You have 3 electrons here. You have 1, 2, 3. And so you can see that if they come together here, 1 and then 1 here, they can make a new bond. And then this other electron here is going to go to this carbon. And so you can see that we have 3 curved arrows, 1, 2, 3, to deal with the 3 electrons there. And so that's a new way to make a new radical, and you've made a new bond, a sigma bond. So here, diradical, this is a termination step. How do I know that? Termination step. So you're going to have initiation, you're going to have propagation steps, and you're going to have a termination step. Initiation, propagation, and a termination step. This is in the mechanism. So here we have two electrons coming together to make a new bond. Do you see there's no new radicals formed? So when two electrons come together, this is a termination step. Radical inhibitors, this is how you control these reactions by adding radical inhibitors or radical scavengers. You'll see vitamin E, like people talk about anti-aging, vitamin E. These are radical scavengers. It's really important, like if you're running a marathon, if you've ever heard of mile 21 and you hit the wall, it's because you're generating these oxygen radicals, and they are now attacking your muscles, okay? And so a lot of times when you're aging, you can get oxygen radicals, and so having radical scavengers in your diet should prevent that because of the oxygen radicals. The other time you see compounds added is like BHT, which you'll see some slides on that. And this is added to like cereals, and when you are closing up your bread, so you take your bread and you don't want it to get stale, it's because you're trying to keep the oxygen environment away from the bread so it doesn't oxidize it. If you see an apple and you eat the apple and you eat half the apple and then it turns brown, so you're seeing the oxidizing environment. Usually that's like a free radical reaction. So you can add these radical inhibitors, and a lot of them are added to food, and they increase your shelf life of your food. Okay, so one of the reactions you're going to have to know is radical halogenation of alkanes. So this is an alkane, and our functional group transformation, FGT, is an alkyl halide. And so how do you do that, and what's the mechanism? Well, you have to add a halogen. So your halogen can be Cl2 or Br2. But now you're going to have to look for H nu or heat. And what happens then, so like bromine, this is the initiation step. We'll say I. And with the heat, or the H nu, this electron splits to give you two bromine radicals. So this is the mechanism. And then you can go into propagation steps. You'll see that there's a P1 and a P2 in order to make this product. So monohalogenation, this is monohalogenation. You can get monohalogenation with bromine. And that's why if you actually work in the lab, this reaction is useful. Okay, a lot of times we teach this, but this is not useful. Okay, now let me tell you why it's not useful. It's not selective. You get lots. You see how you have a 1-to-1 ratio? It's not selective. Not selective. So you can't control whether you're getting a primary or a secondary. You're getting everything. Here, with bromination, this is selective. So this is a useful reaction for bromination. So you can't really control the halogenation. You're just going to get all of them halogenated, you see. That's with chlorine, though. All right, so you're required to write mechanisms. So the first thing you want is initiation, and that means the lighter heat is going to provide the energy to form new radicals. You'll see this with peroxides, or you can see this with halogen Br2 or Cl2, and your initiation step is then going to generate your radical. You can inhibit the reaction by a termination step, a radical scavenger, and this is important. This is different. Even though the pattern, the stability pattern, follows the same as the cation, no rearrangements are observed. So you don't have radicals that rearrange. So no radicals don't rearrange. So we have to not worry about the test. All right, so like I said, we have initiation, propagation, termination. In initiation, two radicals are formed. by the homolysis of the sigma bonds. This always begins the reaction. And then so here, for an initiation step for this would be, you would show it like this, Cl2 and H nu, and you would show these homolytic cleavage, and that's how you would show the initiation step. And then you would do propagation. This means a radical reacts with another reactant, and then to form another radical. So on the reactant side, you need to have a free radical, and on the product side, you need to have a free radical. And if you don't, then you're not propagating. So you got to propagate. So you always got to have a radical generated. So in this case, you would draw out the bond that's going to be broken. So this is going to be a hydrogen, and you would react it with this chlorine radical that you just generated. And you would show the 3 electron flow arrows that are single. That's going to take that. This is going to go at there, and this is going to go there. And this generates a free radical, carbon-containing compound. So you generated another radical, yay. And then we have a new bond here with the chlorine. And so you always have to start with a starting material. We got the starting material here. This is our propagation 1 step. And then notice we got one of the products here, HCl. So now you need a second propagation step. So I'm going to put P2 here, where you take this free radical. Now keep in mind, in propagation step, you have a radical reacts with another reactant. So where's our other reactant? Chlorine. Okay. So chlorine. And to form a new sigma bond and another new radical. So here, this is going to have 3 electron flow arrows. And now we have the new bond. These 2 electrons here. That forms a new sigma bond. And then we have a new radical plus Cl. And so here we made a new product in propagation step. And then termination can be, you can kind of brainstorm on a termination step. So it could be a Cl coming together with a Cl. It can be, we can get a dimer product here where these come together. Okay, so 2 radicals combine to form a stable bond. This stops the reaction. So this is what I just showed you. You see the initiation. You're generating 2 free radicals. You see you have your 2 half arrows. Propagation. Now we have our starting material, our organic compound. We're going to abstract the hydrogen. So this is an abstraction of the hydrogen. It's a secondary carbon hydrogen. So that has a certain bond dissociation energy with it. And then we generate a new radical. So this is P1. And then this is P2, where the new radical will generate the product. And then termination steps can be, any 2 free radicals coming together. Okay, now we're going to talk about bond dissociation energies. Why? Because the one with the lowest hydrogen carbon bond is the one that's going to be abstracted if you have a selective reaction. So this bromination is selective. Like I said, chlorination is not useful because it doesn't care. It's gonna abstract any of the hydrogens. So this is just showing you though that to do this primary carbon hydrogen, it's 410 kilojoules. And these are your propagation step 1 and propagation step 2. When you did your delta H overall, where you take your products minus your reactants, you do this for only the propagation steps. You do not include initiation or termination. And so this is products, delta H equals products minus reactants. And so here you add all this up. So here's your reactants, 410 and 242. And then here you have the bonds form, which bonds form is always going to be negative exothermic. So you have negative 431 and negative 339. And when you add these together, you get an exothermic reaction of negative 118. And here we can do that, 4, 5, 4, 5, 6. So products is plus a negative here. So 6, 7, and another 7. So then you have products minus reactants, negative 770 minus, or we use, well, if you give it positive. So if you have products minus reactants, 7, 7, this is negative plus a 652. I think that should be, yeah, negative 118. So it's exothermic. Okay, so this is a reaction energy diagram. We're generating a free radical. You see that? That's an intermediate. Your intermediates are carbocations and free radicals. So you have to have a valley here. That is an intermediate. So this is going to be propagation step 1, and this is propagation step 2. You see that this is your product, and it's exothermic because your product has a lower energy than your starting material. All right, like I said, chlorination is not selective, so you're going to get all these different ratios. You can use this slide and homework and text to answer any homework questions. I will not be focusing on chlorination reactions because, like I said, not selective, not useful. I do want you to see that it's easier to abstract a tertiary carbon hydrogen because the bond dissociation energy is the lowest. And this is why we get selectivity in a bromination reaction. And so chlorination is unselective. Chlorination is going to be faster. Chlorination is unselective. It gives you a yield lots of different products. Look at this. So if we have propane and we get a 1-to-1 ratio, okay, that means 50% of your products are going to be the primary chlorination product and 50% of chlorination is going to be the secondary. All right, that's not selective. That's not good. If we take propane and we add bromine, we get 99% of the secondary. So it's slower, but it's also selective. And the reason why it chooses to abstract the secondary hydrogen is because the bond dissociation energy is the lower. It's lower than the primary. So, and that's what they're showing you here. The secondary only costs 397 kilojoules per energy. And this is propagation step 1. Because you notice we're generating a radical. And they're just showing you that propagation step 1, even though the reaction is actually overall exothermic, time you add propagation step 2, both of these steps are endothermic when it comes to bromination. And that's propagation step 1 of abstracting the hydrogen. So 29 is lower than 42, and this is, so it costs 29 kilojoules per mole, whereas the primary cost 42 kilojoules per mole. You're going to find that propagation step 1 of chlorination, both exothermic. Okay, and that's why it's not selective. You can't control it. So this is propagation step 1, just P1, and it's showing you that this is your transition state. This is your secondary radical, and see it's lower in energy. And so the rate of reaction is always this height, this transition state, and this is going to have a lower activation energy than to abstract the primary. So it's going to be faster because it has a smaller hill, transition state, activation energy is lower, and so it's going to happen faster. So in the chlorination, you see both of these are exothermic. So this is your propagation step 1, where you generate your primary and secondary radical. Because these are both exothermic, they're not selective. So this is why. And so they're showing you this. So this is your intermediate, and now your intermediate, the free radical, is downhill. So since these are both, so this is your activation energy. Because these are both exothermic, they're not going to be selective. So you're going to get equal. All right, so like I said, we care about the bromination. I do expect you to be able to draw the mechanism. So initiation is going to be the bromine with H nu. You can show the bromination radical. And then propagation step 1 will be the bromine radical plus this molecule. And so you have to ask yourself, because it's selective, where's the, you're not going to get rearrangement. So where is the hydrogen that's going to be the lowest bond dissociation energy for hydrogen abstraction? That's the one you want to draw in. It's going to be this benzylic one, okay? So it's going to be the benzylic. You can look at them. You have an sp2 carbon hydrogen on this ring here. This is not, there's no hydrogen there. You have an sp3 carbon hydrogen here. That is that carbon's bonded. That's a tertiary. So what would that one be? That would be a primary. And then we have the secondary, but this is benzylic, and you can look that up, and this would be a primary. So this bromine radical is going to abstract this hydrogen, and then these electrons are going to go as such. And this is propagation step 1, so you're going to generate the organic radical there, and then you're also going to make the HBr. And then for propagation step 2, you're going to react this with another bromine, and then you get your 3 curved arrows to give you your product, your organic product, which is D, and then you also get the bromine radical. So D is your answer. Okay, what about the stereochemistry of this reaction? It's going to, achiral material will give you achiral or racemic product. You don't have a stereogenic center. So what happens is this free radical is an sp2 carbon. Okay, sp2 carbons are an achiral, right? They're achiral. So you don't have to, you're going to have a racemic. So you're going to get both of them. So because you go through a carbocation intermediate, not carbocation, but anytime you go through a carbocation intermediate or a free radical, which are sp2 carbons, they're not going to be, you don't have a stereocenter. So then whatever you add, so here you add a nucleophile. A nucleophile has 2 lone pairs. It's going to add to the top, and it will add also to the bottom. And here you have a carbon radical. Whatever adds, so if you add another radical, it's going to add to the top, and it's going to add to the bottom. So you're going to get equal amounts. And so that's called a racemic mixture when you get equal amounts. And it's because you generate a planar sp2 hybridized radical in your propagation 1 step. Now, chlorination at a chiral center, like I said, you're going to destroy that stereocenter here, because when this so this chlorine is taking this hydrogen here, now you have a sp2 carbon, and then when you add another chlorine here, it's going to add top, and it's also going to add bottom. So you get racemic. Now, what if it's next door? So if you were to generate the free radical here, next door, the chlorine is going to add from the top and from the bottom. And now you're going to get diastereomers because you have two stereocenters and they are not mirror images of each other. Where do we see this type of free radical reaction? And if you like this kind of mechanism, this is what we see in the atmosphere. Okay, so this is when you get out into outer space, your reaction mechanisms tend to be free radicals. And so ozone, this is ozone. Ozone is important for us. So where do we have ozone? Ozone, the ozone layer actually has a hole in it, which is really sad. And you can look at images on the internet like that, but the ozone absorbs UV rays. So it'll absorb the UV rays, ultraviolet radiation, and it protects us. It's like nature's sunscreen. Well, the sad thing is, like I said, we have a hole in it because we have generated these chlorofluorocarbons. So these are carbons, you see the carbon here, that have fluorine and chlorine on them. So these are chlorofluorocarbons. We see them in refrigerations, propellants, and they're destroying our atmosphere. And this is how, this is the reaction. So what happens to an oxygen radical? It will make ozone synthesis. It combines with oxygen to make ozone. And then ozone with H breaks down to make oxygen and the oxygen radical. This goes on back and forth. And that's why nature does. It kind of does a recycling. Well, the problem with these chlorofluorocarbons, they'll react with the oxygen radical and it kind of like traps it. And then these do not break down and we don't get regeneration of ozone. And so you see here, if you have a chlorofluorocarbon and you generate this chlorofluoro radical, that radical, the chlorine radical here, you see, the chlorine radical is going to react with ozone and this depletes our ozone layer. So there's a lot of science and research that is going into trying to find alternatives to chlorofluorocarbons. A lot of these are they're fireproof. They don't catch fire. So you've seen a lot of chlorofluorocarbons in the fire extinguishers that especially out west when you get the fires. And then this stuff gets in our atmosphere and the water. So there's tons of research that's trying to find replacements. A lot of your furniture, Teflon, these are compounds that are leading to our ozone destruction. Okay, so an allylic carbon, which is right next to the double bond, which you have been familiar with, we've talked about in organic 1, that has a low bond dissociation energy of 364. So allylic bromination is a thing, okay? And this is like a good reaction. This is a good reaction. I've done this reaction several times at Lilly when I worked there because it's a good reaction. It's a way to functionalize an allylic carbon. You see the bond dissociation is less than even a tertiary, 91 kilocalories per mole, which is different because we were doing kilojoules before. So the book has switched. But it's more stable than a tertiary. And the reason why is because the allylic carbocation can do resonance. See my double-headed resonance arrow? So this will go here, and this will go there. And this is your allylic radical, which is resonance stabilized. So, like I said, this is showing you that. Delocalizing the electron over the carbons. All right, so what is this reaction? this reaction, now, this is a peroxide. And so you don't even have to have H nu. So I'm going to tell you a little story. A long time ago, this one scientist was trying just to do this reaction, HBr. And so if you have HBr with this, then you get electrophilic addition. So this would be the H goes there to generate your secondary carbocation, and then the bromide comes in. And so that's a double-headed arrow here. This should be a double-headed arrow as well. So make that correction. So one, two. So this is the product that you would expect to get. This is electrophilic addition. So the scientist was trying to do this, and the scientist kept getting this product. Okay, so what happens is they didn't know, but the bottle was old, and sometimes old bottles generate peroxides. They're old, they generate these peroxides, and what was happening is they kept getting this product. They kept getting this product, okay? And so D is the answer here. So how does that happen? Well, the initiation, this will just generate a peroxide, okay? And then what happens is this will, propagation step 1, this peroxide will react with HBr to take that hydrogen, okay, because it's in the bottle. This is happening in the bottle. So this makes methanol and the bromine radical. That's propagation step 1. And then propagation step 2, you have this compound here plus the bromine radical, and you get, actually that's not right there. It's going to go here. You got to get the more stable radical. So there's the bromine, and now you have your radical here, which is a secondary carbon. Okay, so there's where your free radical happens. And then propagation step 3, this is one of those, you're going to, with the HBr, now it picks up the hydrogen. And so there's your bromine. So that's how you get the D product. So this is how we actually learned about free radical reactions, because of this old bottle of hydrogen peroxide. And what happened was, it was like, no, they're arguing about it, can't be, but they kept doing it and kept doing it and did it. And then they went and they ordered more HBr, and they couldn't repeat it. But then they realized, oh, we're generating peroxides in this older bottle. So if you add peroxides to your bottle, you get, and this is called the anti-mark addition. So this is anti-mark hydro bromination, because you're adding a hydrogen and a bromine, but this is the anti-mark. And so you're going to have to pay attention to that. If you have these peroxides, you don't get this electrophilic addition, because it goes through a different mechanism. It goes through the free radical mechanism to give you the anti-mark product. If you want to actually get allylic halogenation, then you use these reagents. So if you see MBS, and you'll have to either say H nu, or I call it ROR. That's just could be something like this. With MBS, you're going to get allylic halide. So there's your N-bromosuccimide. This is a nice little white solid, and what it does is it keeps from getting the anti-mark. The anti-mark hydro bromination of your double bond. So we just saw that we got the addition to this double bond, but this is allylic bromination. So this is allylic. So how do we get allylic bromination? I told you it's the thing. We used to do a lot of allylic brominations. You need to have MBS, okay, this bromosuccimide. And the reason why it works is because this keeps a little bit of the bromine. So you get the bromine to abstract the hydrogen. So what's the first step that's happening then is this bromine will abstract this hydrogen to generate an allylic radical. And then, so what happens then is it can then make more bromine. Okay, so then you get the bromine added there. And so you don't actually generate the anti-Mach hydrobromination. And so you see this, you get, this keeps the concentration down low, so you get the bromine, and then the bromine will take the hydrogen radical. This is propagation step 1, and then this is propagation step 2, where you generate more of the bromine radical. You can write, if you're doing your mechanism, you can just do BR, or you can draw the whole structure out. But that's typically the source of the bromine. So, anyway. So what you need to do here, this is addition. So this is electrophilic addition. So you need to be able to look for this. This is going to give you the anti, so I would expect you to do the dash and wedges. This goes through the bromonium intermediate, if you remember, from organic 1. And then the bromine radical will open up. And so that's how you get vicinal dibromide. If you have MBS, that's your source of bromine radical. So you could just do, okay, that's after you get initiation. And then you might want to draw in your hydrogen there to show your propagation step. And so you get this intermediate, which then will go and do another free radical abstraction to give you your product. And that's how you get allylic bromide. So why does MBS favor substitution over addition? And it's because you get a low amount, or you get a low amount of BR. And so you can generate that radical. But when you add just bromine straight, there's so much of it, you're going to get your bridged bromonium ion. So it's all about the concentration of keeping the bromide low. And so you get the bromine radical rather than the bromide. So here you have a hydrogen. So MBS, you can do your bromine, and then you can draw your intermediate. I think it's important to be able to draw that intermediate. And then what they're showing you here is you get some of this competing because of the resonance structure. So be sure to look for that when you're dealing with allylic compounds, that you need to draw the resonance structure, and then either one of these can go to make a product in your next propagation step. And that's what this is showing you because of this resonance structure. You're going to get allylic bromination on the tertiary and on the primary. Okay, which of the following steps is a correct propagation step? So propagation step, make sure you read these questions twice, and allylic bromination. So bromine radical is the initiation step, and then you want to draw in your allylic hydrogen. And so then propagation step 1 would be plus HBr. That's a propagation step 1. And propagation step 2, keep in mind you might want to do your resonance structure here. I think you'll realize that they're all the same. And then propagation step 2 would be the product plus the bromine radical. Now we can look for it. This would be initiation step. 2 radicals is a termination step. So this is termination. And let's just see, is B one of them? So propagation step 1, you have the bromine radical. So that's correct. And then you generate this. So B is definitely a propagation step. And then here, the next one is, this is your starting material. So B is your answer. Okay, I kind of hinted that we use BHT, butylated hydroxytoluene. This is butylated hydroxytoluene in our food, and it increases our shelf life. I also told you about vitamin E. Vitamin E is a radical inhibitor. And the mechanism, this is just showing you a mechanism. This hydrogen is has the lowest bond dissociation energy of all the hydrogens on this compound. And so it will abstract a hydrogen. And then you have 5 resonance structures, which stabilizes that free radical. And so that is why phenols are good radical scavengers. Okay, this is showing you we can add this free radical to a double bond to get a new radical. And this was what I was showing you with the peroxides, and I told you about the story. Here, your initiation step is, you have 2 initiation steps. One is generating this free radical, and then that's initiation step 1. And then initiation step 2 is this peroxide then will react with HBr and abstract the hydrogen to make the alcohol and the bromine radical. It is this bromine radical that becomes a propagation step, because what do we care about? We care about our carbon containing. And so then if you have this, now it's going to add to generate something that looks like this, where the bromine's going to add, and then you get this free radical. Now keep in mind, these would be equally, this is tertiary and the other would be tertiary, but you want to get your more stable free radical. So this is going to give you an anti-mark product of hydrohalogenation. So if you just use HBr, you're going to get electrophilic addition. This is going to go Markovnikov. So the bromine is going to add to the more stable carbocation. So you get the carbocation intermediate. For when you have peroxides and with your HBr, it's going to be the anti-mark product. So the bromine is going to add to the least substituted, the primary. This adds to the secondary carbon. This adds to the primary. So this would be your secondary carbon. This is your primary carbon. What's your intermediate here? Your intermediate would be bromine adds first to generate the secondary carbocation radical. So these are your intermediates for the first one, and this is your intermediate for the second one. And so they're showing you this. You have 2 initiation steps. The first one generates the peroxide, and the peroxide then will abstract a hydrogen from HBr to generate the bromine radical. Then we have the propagation step, where we make this intermediate the secondary radical, because bromine adds first. And then this is your propagation step 2, that you abstract a hydrogen. Hydrogen adds second. So in this, the hydrogen adds second. So hydrogen adds second, bromine adds first. And this is the anti-mark halogenation. That's the opposite of electrophilic addition that gives you Markovnikov's addition, because the hydrogen adds first to give you the more stable carbocation. And then the bromide will then come in and add. Regiochemistry, this is the anti-mark. You're going to see the preferred path because the bromine adds first to give you the more stable. This one, you will not get the less stable radical. And so radical addition, you're going to get the anti-mark Kovnikov product. And ionic addition, where you get the carbocation, you get your Markovnikov product. This is showing you that HCl doesn't add because of the bond dissociation energies. Basically, you don't generate your chlorine radical with the peroxides. So this is, you only have to look for this for HBr. Okay, so NBS. NBS generates low concentrations of bromine radical, an H nu. So that's your initiation step, and you can just go straight to that. And then you want to be able to draw your mechanisms, which is the propagation. So this is allylic bromination. You should see that. And then that should tell you that you want to draw in your allylic hydrogen for your propagation step to abstract. So this is going to abstract the allylic hydrogen. And then you have to be cognizant of the resonance structure. And so then propagation step 2 with the, you can just do BR, or you can do in bromosuccimide, but here we show this electron. I would redraw it after you draw arrows. The second propagation step. And then here, propagation step 2 with the BR. BR plus BR. And then you can see, okay, we had allylic bromination. This is one of them. 1, 2, 3, 4. 1, 2, 3, 4, and B. So A and B are your products. What is the product for the following? Draw the mechanism. Okay, so we have peroxides here. So this generates an oxygen peroxide that can then initiate the bromine. So this is a bromine radical here that adds first. Now this is not going to take a hydrogen because of the low concentration. This one's going to add to the double bond, and so you're going to add the Br there so you can get your free radical, which is a secondary free radical, and then this is going to generate with HBr. And would you get some allylic? Probably you would, but doing the concentration, you're going to get this 1, 2, 3, 4, 1, 2, 3 anti-mark. So this is D. It'll generate more bromine that will add first, and then it's because you got the HBr, the initiation will add H to the free radical. All right, so that pretty much wraps up the reactions for chapter 13, and you should have a POGIL exercise with that.